No problem. Our pleasure.
Yeah. Bill, do you want to lead us off with a question? I'll put you on the spot.
Okay. Yeah, this is not optimal, but I noticed in your technical report you talked about having problems with your manufacturing of your tubes with some out-of-ground conditions and things like that. Can you kind of expand on that a little bit more and tell us what you're doing to correct that for future tube manufacturing?
Sure. I guess, Luke, do you want to take that one?
Sure, I can speak on that. So we had issues not only with the supplier of our tubes, so it wasn't the most cooperative supplier. We used Proline Composites, and even though they produce very high quality body tubes for our rocket, there were a lot of delays and difficulties in working with them. So in the future, we intend to either reevaluate that working relationship with Proline Composites and reach out to a different supplier, or we will threaten them with whatever means we can to get better service from them to complete a little more promptly next year.
Yeah, I think and to address the other question you had about the out of round, it wasn't that it came from the manufacturer out of round. It was that actually on recommendation of our subject matter expert, our L3 mentor that joined our team, is actually Mr. Greenapple with us today. He recommended that we cut the fin slots all the way to the aft edge of the airframe to make it easier to slide the motor tube and the fins as one complete assembly into the rocket from the aft end. It would be kind of difficult to slide the fins through the fin slots and then slide the motor tube in and try to get epoxy down there. You could do it, but it would be difficult and cumbersome. So what it actually ended up being is when we cut those fin slots to the edge, there was no more, we lost the actual rigidity of that 1.5 inch, piece of fully circular G10 at the aft end. And where they were cut at the fin slots, essentially those four quarters now kind of curled in. And that's because they're manufactured on a mandrel, they're filament wound. So it's got this internal tension that wants to pull it in. And, although it was kind of, nerve-wracking when we first saw it, it wasn't a difficult thing to overcome. Once we decided to continue as we planned, build the motor housing with the fin, as one fully assembled unit, slide it in the back, and then we just used a ratchet strap and a centering ring, and we just clamped it down over that centering ring, and that brought it perfectly back into round. We put our aero epoxy fillets on the fins, and it's all beautiful now. So, and then you asked, I think, if we were to do it again in the future. Quite honestly, I think the difficulty in trying to assemble it the way we were originally thinking would have been even more difficult. So I still rather deal with the out of round airframe and clamp it while it glues than, having not installed it as a complete assembly, because trying to build that assembly when it's already inside the outer airframe would have been very challenging, and I wouldn't have as much faith. I don't think anybody here would have as much faith in the structural aspects of the assembly had we not been able to get a full clean fillet on the entire unit.
Yeah, I mean, there are ways of handling that without having to cut the fins. One of the things I did on a recent project, just to give you an example, is when I put the motor tube in, I just had the forward centering ring in the motor tube, epoxied that part in, left that out, and then when you put the fins in the fin slots, then you can use like a big 50 milliliter syringe, like you can get them at pretty much any feed store, with some plastic tubing, and then you can use that to inject your inner fillets around the fins, and that works pretty good. You have to kind of do it in 3 stages, turning the rocket each time so that the epoxy settles to the bottom part of that. But that's, and then once that, all those internal fillets were set, then you just had it in the aft centering ring. And in my case, I had a thrust plate as well that did it. So, that's just a technique, that you might consider in the future.
Yeah, we looked into that, and we also looked into, there are a few people who actually said to drill holes through the outer airframe and use a syringe with a hose. And, at the end of the day, they're all acceptable and they all work. But, I almost feel like this one, now that we did it once, would be more confident doing it again in the future. So I don't know. Unfortunately, this is my last year at Lehigh, so I'll leave that up to the group to determine what they think is best next year.
Okay, yeah, that's fair enough. I mean, there's, it's in rocketry. There's a lot of ways to do things, and everybody has their opinion about what's the best one. So, but as long as you can, make the good case, then, I don't have any problem. Holly, do you have any questions off the top here?
Well, I got tagged onto this a little late, so I didn't have access to the report, unfortunately. So I don't have as much background. Can you just give me a 10,000-foot view of your rocket? Just a quick blurb.
Yeah, well, so it's a 6.5-inch diameter G10 rocket. The entire airframe and the fins were supplier manufactured, but essentially all the interior components, in terms of electronics design, where we would place everything, fin shape and material, all that was designed by scratch. It has a calculated apogee of 10,033 feet. Using New Mexico, weather conditions, we actually plan on launching it in about a month up in upstate New York. So hopefully, then we'll have some actual data to provide, for validation purposes. But that's it's a M1450 motor. It's about 77 pounds is the weight.
Okay.
760 some feet per second max velocity. And I'll turn over to the other guys here because they have better systems knowledge if you want to know more about the payload specifically or the motor specifically or electronics.
Okay.
Yeah. One thing I noticed is that you used 3D printing in part of your payload and other places, and that you're using PETG, which generally is a pretty good choice. But I will, have you thought about the kind of heat that it would be subjected to out here in New Mexico? I live out here, and I printed up some PETG stuff to put in my car to hold my sunglasses and things like that. And boom, after a day, those things, the heat had completely deformed those things, and they weren't any good anymore. Had to go to a different design. So how have you, what process did you go through to think about the heat issue?
Well, actually, my experience, the heat issue, I hadn't thought about out in New Mexico, actually. The filaments we have available for us right now are just the standard PLA, ABS, PETG, and out of the available filaments, we came to the conclusion that PETG had, one of the better overall resistances to what we would be facing. But with your input and not having that experience of just things melting in the car out in New Mexico, I will look into that.
Yeah, and even if it doesn't melt, you'll get warpage.
So
Yeah,
one thing I can add on to as the lead for the payload design is it was very specifically designed and very highly toleranced. So a lot of the the 3D printed parts were compacted and held tightly within the rocket within a foam and G10 enclosure. So any issue of warping would hopefully be mitigated by the pressure applied by the foam and the enclosure for the payload itself. But that is definitely something that we should take into account for next year's competition.
Mhm. And what is your payload?
So our payload, we ended up opting for a sort of a boilerplate payload, but we added a little bit of special engineering touch to it. So we made it variable mass. So not only did that allow us to fine tune our apogee and match with our simulations, but also change the center of gravity and of the rocket, which can be helpful to also change the apogee and change other dynamics of the rocket. And so that was accomplished with just numerous stainless steel rods, 3-inch stainless steel rods. A lot of them, I think it was 45 in total, 15 per payload CubeSat unit.
Okay.
Yeah, so to add on to that, and if there's no additional questions on that, so that was sort of our jumping point. This is our first year with a successful entry into the competition. So we figured this was a good place to start in designing a more advanced payload and not just simply filling it with sand and using that as boilerplate. So we hope to be able to have a platform that we can easily build off of in the coming years.
Yeah, that's a good way to start. Very good.
Can you tell me a little bit about your nose cone? How did you manufacture and affix your nose cone?
That was part of the. Oh yeah, Abiola, you go ahead and speak to it.
For our nose cone, we actually ordered it same from the supplier, Proline Composites. I believe we just chose the basic shape, a guide. With the simulations we did, we felt that choice for the shape was the best. So we didn't actually manufacture the nose cone ourselves.
Okay, but what did you do? What did you do to determine that shape, and what was that shape?
The shape was Ogive, and I believe maybe Trevor can speak on this, but I believe we chose on the shape based on the simulations we ran and the research that we did. We believe that shape was the best.
Okay.
Yeah, so we were very persistent with, cross-checking all the decisions we made with the simulations. So the nose cone was definitely one of the first earlier on components we decided to, finalize, because we had to order the airframe, which included the nose cone very early on. So we kind of started building around there, and then through a lot of research and also through running some very early on simulations, we determined that the ogive shape would definitely serve us best because of its aerodynamic properties.
Yeah, and if I could add on, the best way to describe kind of our process was we started with this big, with an idea of what we wanted to achieve operationally, and we got, we had to settle on a starting point. So we found an airframe that we believed would get us an operating envelope that encompassed our end goal, which was 10,000 feet. And then we immediately started running simulations and refining them and planning where we would put certain components with essentially estimated weights with 3D models and stuff like that. And then as we started to build those actual assemblies, we would weigh them out and update those weights in the simulation to essentially get closer and closer to what we actually have. And at the end of the day, now where we are is we have an assembled unit that has an operating envelope that was kind of refined into that 10,000 foot ideal. And we had a lot of help, I should add, from our suppliers. We pulled them into the process. We pulled in Proline because he certainly had some experiences with rocketry before. We pulled in Fruity Shoots. We pulled in Tinter Rocketry, who supplied our CO2 ejection, and they all provided input as to how to best use their products in our design. So some stuff was developed internally, but it was definitely backed by the recommendations of the suppliers as well. And in terms of length and shape of the nose cone, that was a group effort with that supplier line.
Okay, all right. Well, thanks very much. I got to call time because we're at the end of the period. I appreciate your responses and the hard work that you put into this project. So you're free to go, and we'll get our next team in. Thank you very much, gentlemen.
Thank you for having us. And if you guys have any questions, you could send us an email, and we'll definitely answer them for you.
Thank you.
Okay, will do.
Thanks, everyone.
Nice job, guys.
Thank you.
Thank you.
Good afternoon.
You may be safe
Hey.
reporting for answering your questions.
Yeah. All right.
Welcome.
Cliff, welcome. Cliff, do you want to, or Holly, you want to start us off this time? No.
I'll be happy to start us off. I know we pulled Holly in, so I appreciate it very much. And so welcome, team.
Yeah.
Appreciate the time and appreciate your flexibility to meet with us, and a little bit later than planned. So maybe you can just start a little bit for our Q&A. Just give us a small overview. What is your target altitude? What is your motor type? And what is your payload?
Sure. Well, our target altitude is 10,000 feet. Our motor class is type M, and also our payload is a nanotechnology-based sensor for measuring air pollutants.
Okay. And the motor, it's a commercial off-the-shelf motor, or have you built your own motor?
It is a student researched and developed solid rocket motor.
Okay.
Yeah, we develop our rocket motor.
I see. And have you flown this rocket before?
No, we have not.
No, only simulations.
I see. What about engine testing? Have you done any motor testing, static firings?
All right. So in regards to that,